Okay, so this week we are going to talk about correlation. And when you hear, a little correlation bell, that's good. When you hear correlation, I'm hoping you think scatter diagrams. And I'm hoping you remember back to the happy days of GCSE when we used to plot a scatter diagram for two things that we thought were probably related. So it might have been, I don't know, shoe size and height, or height and arm span, or temperature on Woolacombe Beach and ice creams sold. And we plot some points and we say, right, okay, we've got a pretty good correlation there. So I'll tell you what, I'll draw a line of best fit, sort of something like that. And I can use that line of best fit to make a prediction. So if I've got a value here and I want to know what this would have been, I go up and across. And if I've got a value here and I want to know what this would have been, I go across and down. GCSE correlation in a nutshell, really. We do the same at A-level. We're a little bit more sophisticated. So we are a little bit more deliberate about every step along the way. So the first thing is our axes. So when we think that there are two things which are related, that's what correlation is about. It's about two things which are related in some way. Normally, one of those two things is the thing that we suspect is the driver. So it is not sales of drinks on Woolacombe Beach which is affecting temperature. It is the temperature which is affecting the sales of drinks, isn't it? So the thing we think is the driver for the relationship, that should always go on our x-axis, and that is called, the scientists all said in one accord, the independent variable. Yes, I'm sure that's what you think. So that's called the independent variable. So we always put our thing that we think is affecting the change, or the thing we're adjusting. So back to your science experiments, hanging weights on a spring, the weight would be the independent variable, wouldn't we? So this is the thing that we are controlling, or that we think is affecting the other. So the independent variable is the thing that we're controlling, in the case of hanging weights on the spring, or the thing that we think is having the effect, in the case of temperature. Sometimes this is referred to as the explanatory variable. You're not expected to remember both, but those mean the same. So the thing on the other axis is called the dependent variable, unsurprisingly. And that's the thing we think is being affected. The dependent variable is sometimes referred to as the response variable. So explanatory and response. So the response variable, the dependent variable, the thing that is being controlled. So that, in my case, example, would be the length of the spring, if you're hanging weights on it, or it would be the number of drinks sold on Woolacombe Beach. And we would still plot our points and we would draw a line of best fit. Well, only if there is correlation. So we'd only think about a line of best fit. So we'd only draw a line of best fit if there is a correlation. If there is a correlation. So let's not put the cart before the horse. Before we do anything with lines of best fit, let's decide how we can evaluate the extent of the correlation. And in the old days at GCSE, we'd just say, well, the points are sort of lined up in that direction, so that's a positive correlation. Or the points are sort of lined up in this direction, so that's a negative correlation. Or they're just all over the place, so that's no correlation. And we might add a bit of a commentary on there, so it might be a strong positive correlation or a weak positive correlation. Well, the good news is that at A level, we have a way of measuring correlation. So that's the first thing I want to introduce to you. That is measuring correlation. So that's my cheeky subheading. There's a couple of ways we measure correlation. Only one of them features on the A-level syllabus. Some of you who do other subjects might have come across other measures of correlation. Anyone do psychology? So some of you might have come across Spearman's. Do you do Spearman's in biology? Right. So the way we measure it in, we used to do both actually, but the way we now use is a measure called the product moment correlation coefficient. Which is mercifully abbreviated to PMCC. And is given the letter R, so that's even better. And it is a measure of linear correlation. And by that I mean it is a measure of how well the points line up. So if you plot a scatter diagram and the points line up perfectly in an uphill direction, when you calculate PMCC, you will find you get a value of 1. 1 indicates perfect linear correlation. If you plot a scatter diagram and the points line up perfectly coming downhill, and you calculate R, you will get a value of -1. In reality, with real life data, you never get 1 or -1, but you could get something that's pretty close to 1 or pretty close to -1. That would indicate that we've got a pretty good correlation. And if there is no pattern at all, then you'd get PMCC of 0. Now this week, I'm going to do as much of the content as possible, and then I'm going to do a little bit of explaining if we have time. So I'm going to explain how R is calculated. I mean, the use of the word product implies multiplying. The use of the word moment perhaps implies distance away from a point, because we came from something mechanics. And it's quite a neat explanation, but we don't need to understand it. So I'm going to get through the content first this week, and then if we have the luxury of a bit of time towards the end of the week, I'll chat about how it's worked out. The good news is that to calculate R, we need to know nothing, we just need to know how to do it on our calculator. So on old spec, it was a formula that we had to use. That formula has now disappeared from the formula sheet, and we just use our calculator. So let us calculate a value of R using a set of data. So we need our calculators to be in statistics mode. And I think we're on page 6, but I don't know exactly. We're at the bottom of page 6, question 2. So this is in Statistics and Mechanics Year 2, which is on OneNote and on Active Teach. So we're page 6, at the bottom of page 6, question 2. You've just got a set of data. That data is called bivariate data, which is a posh way of saying it's a scatter diagram. Bivariate means 2 variables. So all you do is you put your calculator into stats mode and enter that in the first 2 columns. First column is your x values, second column is your y values. So I've got my x values in the first list and my y values in the second list. Doesn't matter if I haven't got them all in. And I note that although I'm talking x and y, they're using v and m. And it doesn't actually matter for the calculation of r which way round you put the data, if you put the data in the different columns. So here's what we do. We go to calc. And this topic, and I'm going to explain why it's called this, is often referred to, instead of correlation, it's referred to as regression. So we go to reg, short for regression. And we just choose x, which means we're dealing here with a linear relationship, straight line correlation. And it doesn't actually matter which of these two buttons we press, but you'll see later on in this lesson why we're going to press the a plus bx. It doesn't actually matter, you get the same answer. We get a lot of information which we do not need, with the exception of one value, and that is r. So this is the calculation of r. This is a measure of how well those points line up. So that question, if we had drawn a scatter diagram, we're not going to, but if we had drawn a scatter diagram, that's the value of r, which indicates that you've got a pretty good positive correlation. So I said 1 never happens in reality, but 0.9-ish, that's really strong positive correlation. And if it's negative, that would be negative correlation. So when we say in part B, use calculator to find the value of the product mode correlation coefficient, we've done that. And then if it then wanted to say comment on the correlation, well, it's nearly 1, so I would say it's a strong positive correlation. Okay? So we've got a value of r which indicates that in this set of data we have a strong positive correlation. That's a big tick in the box. That means we can now go on and draw our line of best fit. So, I'm only going to do one r example because we'll do some more later on. But now we've calculated r, so we've measured correlation, and we've calculated this value, which the calculator's done for us, first developed by a mathematician called Pearson. Quite a clever calculation, which I will show you. I think by Friday will be done, so I'll be able to, no, not by Friday, because you're not here Friday, by early next week will be done, so I can, in fact this will be our last lesson next week. Please come next week, it'll be fun. Right, so we've measured correlation, so now we can draw a line of best fit. We only do this if we've got a strong value of r. There's no accepted point. They don't say, right, you can't draw a line of best fit if r is less than 0.5 or less than 0.8. There's no value like that. What it means is that the predictions made from a line of best fit become more reliable the higher your value of r is, the closer your value of r is to 1. So, I have good news and I have bad news. The good news is we no longer have to draw a line of best fit. We're at A level now, we're proper mathematicians. So what we do instead is we describe the line of best fit with an equation. So rather than drawing a line of best fit, we are given an equation. And the good news is that we are not expected to do any calculations. We are given the equation of the line of best fit. Again, that's a new spec feature. Used to feature On the old spec, we used to have to calculate it. Now we don't need to. So rather than drawing a line of best fit, we are given its equation. That's the good news. The bad news is that up until now, when we write down the equation of straight lines, we write it like this. Unfortunately, with this topic, it's written like this. There are two changes which completely mystify me. I have no idea why they do it. They have replaced the m with a b, but it's still the gradient. They have replaced the c with an a, but it's still the y-intercept. And they've written them the other way around. Go figure. But when we are given the equation of a line of best fit and asked to use it and interpret it, we need to remember that those two things are still the same as they are with any normal equation of a straight line. The coefficient of x tells us the gradient, and the y-intercept tells us, a tells us the y-intercept. Now, bizarrely, the book, we didn't do any correlation last year, but the textbook splits this topic between year 1 and year 2. Oh no, my session's timed down. Oh dear. Right, okay. Which means I can't. Hang on a minute. So we have to look in the book 1 for this, and unfortunately the book 1 is with the year 12s. So I'm going to quickly open book 1 here. Apologise for this. Come on. Okay, so this is how a question would look. So we are given a set of data and we are given the equation of the line of best fit. And in this case they've done a little sketch for us, but that's not often included. So let's pretend you can't see this. How can I tell from my equation of the line of best fit that I'm dealing here with a positive correlation? How can I tell I'm dealing with a positive correlation, George? Because the gradient's positive. Yeah, gradient's positive. So I know that a gradient of 0.64 is positive, so this is an uphill line. We're not measuring R here, but we would have, before we got to this point, we would have measured R just to confirm that it's okay to go ahead with the line of best fit. But we're assuming that's okay. So let's try and in this example interpret what the two values in the equation of the line of best fit tell us. So we're dealing here with x is the gestation period, so that is how long before the baby was born, and y is the head circumference, something very dear to my heart. I have a particularly large head. So the head circumference of the babies who were born at that time. So what does 0.624 tell us? The gradient of 0.624. What do you reckon, Grace? What does a gradient of 0.624 tell us happens every time we move along one unit on the x-axis? That's right. So in the context of this example, 0.624 tells us that for every extra week before the baby's born, its head grows by, or its head circumference increases by 0.624 centimetres. And what about the 8.91? What does the 8.91 tell us? So, Beth, what is 8.91? What was it in terms of the graph? What is it? What is
Where
it?
it cuts the y-axis.
Which cuts the y-axis. That's right. Yeah. Where it cuts the y-axis, not here because this is 30, but at 0. So what that tells us is, at 0 weeks gestation, the head circumference would be 8.91 centimetres. Now, of course, that's a nonsense value. You can't make a prediction for that. But if we were to extend the line of best fit backwards, that's where it would cross the y-axis. Okay, we've got our equation we've got our equation of line of best fit. So can I get you to use that equation to estimate the head circumference for a baby born at 39 weeks and 30 weeks? All that means is work out y when x is 39 and when x is 30. Okay? So this is on page... no, so this isn't in that book. So this is in book 1, and it's page... it's not 73, because those page numbers don't line up. Hang on a minute. Page 64 in the first book. Book 1, Stats book 1. So, if you were asked to interpret 0.624, it wouldn't be acceptable just to say that's the gradient. You would be expected to say it's the increase in head circumference per week, or something along those lines. If you were asked to interpret the value of 8.91, it wouldn't be sufficient to say that's the y-intercept. You'd have to say that's the head circumference at 0 weeks. So often we're asked to interpret those values. So when x is 39, Tegan, do we get a value for y?
No.
Lily, got a value for y when x is 39? Say again, sorry? 0.246. So I'm going to say it's around 366, 34.2, and that's centimetres. And Charlie, when x is 30? Okay, so all we've done there is we've just used the x value in the equation, and that's the equivalent of what we used to do at GCSE, where you draw your line of best fit and you go up from 39 and across, or up from 30 and across. This is the more sophisticated way of doing it. Now, we're asked to comment on the reliability of these estimates. Well, the first thing would be, what's the value of R? Now, we've skipped through that step, so let's assume that R is a nice, strong value close to 1. That's the first thing that affects reliability. But there's something else that affects reliability. Could anyone suggest why one of these predictions in particular has a problem? Yes, Lily?
Babies like 0 weeks old is still got egg.
Okay, yes, so certainly going back to 0 would be pointless. But what about these two predictions in particular for 39 for 30 weeks?
30 is outside the range.
Yeah, absolutely, yeah. We haven't got any data anywhere near 30 weeks. So, you know, although it looks like there's a linear correlation in these range of values, we've no idea what happens around 30 weeks. So this prediction, 39 weeks, this is a reliable prediction because it's slap bang in the middle of our data. 39 weeks, it's, you know, bang in the middle there. And we've even got a value for 39 weeks, which would be slightly different to this because obviously lines of best fit don't go through all the points. So making a prediction within the range of values has a name that we've come across before. It's called interpolation. But 30 weeks, that's outside the range of values. It's not too big, but making a prediction for too big would be nonsense as well, because, well, obviously we would hope that before long the baby's been born. But it's certainly in this case it's below all the values, so this is unreliable. And it's unreliable because it's outside the range of values, and that is called extrapolation. It's a good old maths word, isn't it? It's a word we use at GCSE as well. So making a prediction outside the range of values is referred to as extrapolation, and it is unreliable. So comment on the reliability of these estimates. You would be expected to say for 30 weeks it's unreliable, and I would use two things. I would say I'd use the word extrapolation, but then I'd explain what I mean by that. I'd say it's below all of the values that we've got plotted. So I wouldn't just use the extrapolation, I'd say it's below. Now, this last question is a bit of an odd one. We have predicted head circumference for a particular number of weeks. And we're now asked to predict the number of weeks for a particular head circumference. And it says, why is that not suitable? Well, in order to do that, we need to understand where this line comes from. We don't have to calculate it, we'll always be given it, but I think it's important to understand where it comes from. Firstly, it's referred to as a regression line. What does the word regression mean? And secondly, it's called the y on x regression line. Why is it called the y on x regression line? Well, let's talk about regression firstly. I mean, I've got a tale of woe for you, really. I mean, I've started playing golf recently, and my handicap at the moment is 19. That means in a round of golf, if I'm playing normally, I'll go round in 19 more shots than I need to. So that's just over one extra shot a hole. It's not bad, it's not bad. And some days I go out there and I do much better than that. And I think, this is it, I've arrived. I'll be in the pros before you know it. And you know, I go home and I'm happy as Larry. I'm such a joy to be with when I've had a good round of golf. But then the next day I turn up at the golf course thinking, this is it, I'm a better golfer now, you know. And I'm a disaster. It's much worse. It's much worse. And the fact of the matter is that in most situations where you've got something which is largely dictated by randomness, some days you're good, some days you're bad, but if you play enough golf, you're always going to average out somewhere around here in the middle. We always regress to our mean. So regression to the mean is a phrase that refers to the fact that if there's an expected value of something, some days it's going to be better, some days it's going to be worse, but if you take enough days, you're always going to end up in the middle. And that's why we can use lines of best fit, because this line of best fit doesn't go through every point. You get some babies at 38 weeks whose heads are bigger than you expect, but there'll also be as many babies whose heads are smaller. And there's somewhere in between, which is the typical value. And the line of best fit is a way of representing that. There's a famous example of a misunderstanding of regression, which often features in sort of videos about this. The Israeli Air Force where that comes from. But the Israeli Air Force experimented with praise and punishment for their pilots. I'm really glad I'm not in the Israeli Air Force. Well, firstly because you'd be, have to do things to Palestinians, which I'm not very keen on. But there you go. But so they found that if they had a pilot who had done really, really well, and they praised them for that. I don't know how you do really, really well as a pilot. Perhaps your bombs had dropped right on their targets, I don't know. Hopefully they're just training, hopefully. But if they praised a pilot for doing really, really well, they found the next time they flew, they didn't do as well, they did better. They did worse. A bit like me in the golf game. And then they found that if they took pilots who hadn't performed very well and they punished them in some way, perhaps they removed privileges or paid them less, they found that the next day that pilot flew, they did better. So they mistakenly thought that this was because it's better to punish than it is to reward. Because if you punish people, they get better the next time. If you reward people who've done well, they tend to do worse next time. But of course that's nonsense. It's regression, isn't it? If you have a really good day one day, better than your average performance, the chances are the next day is going to be lower, because we all regress to the mean. So there we go. The Israeli military knew very little about regression. Fortunately, we do. Now, of course, that's not always true, is it? Hypothesis testing is about saying, this is what I think my handicap is at the moment. I think my handicap is 19. But of course, it might be that I start playing rounds of golf that are getting better and better and better. Is that because I'm about to get a whole load of rounds which are rubbish, or have I actually got better? So sometimes things change, but there we go. So that's regression. Sorry, that's a very long explanation of regression. So why is it called the Y on X regression line? Well, I want to show you how the Y on X regression line is formed. I'll try and show you briefly, because there's a lot of me talking, but there we go. You don't need to, and this is not something you need to know, but we'll do it all the same. So, sorry, let me just get it open.
Are we still making notes on it?
Well, it's up to you. You probably don't need to. I don't know. You might see. So here's a scatter diagram. Okay. So I don't know what we're recording here, but let's say we make a number of measurements and we plot those measurements on our scatter diagram, and lo and behold, we get a bit of a positive correlation. And we measure R, and it confirms that we've got a positive correlation. Okay. So we try and draw a line of best fit, and in the past, what we did was we tried to sort of draw a line that best went through those points. So we would sort of, I don't know, I tend to say, try and get as many points above the line as below the line. What the lines of best fit that we're told about at A level do is this. They say, okay, we're going to use this line of best fit to make predictions for Y. So what I'm going to do is I'm going to work out how far away from my line of best fit each value is in the Y direction. And I'm going to try and minimise those. So I'm going to try and sort of move the line up and down so the total of these lines is minimised. Now, of course, the problem we've got there is if I do that as a sum, I've got some differences which are positive, some differences which are negative, so the positive and negatives tend to cancel each other out. We have that problem also with standard deviation. So what we do with standard deviation, we do the same here. We square those differences. Now, why we square them rather than take the absolute value, I'm not particularly sure. I think it's because if you square them, bigger differences have a stronger effect. So what I can then do is I can say, right, so this little bar here shows me the sum of all those differences squared. So I can start fiddling about with these values to try and minimise that difference. So there's two there. Oh, right. That seems to be pretty much the minimum value. And that gives me the equation of my line of best fit. Now they do it a different way to us. This must be from a different country, but this would be 3.44 plus 0.64x. I can actually see what the actual one would be for my data. That wasn't far off, But the regression lines that we're given are calculated by minimising the Y errors. If I calculated the X errors, So if I did my lines this way and squared those differences and did the same calculation, I'd get a different line of best fit. Not super different, but it would be different all the same. So the reason that in this question, we can't use or we shouldn't use the regression line to predict x values for a y value is that regression line has been calculated to minimise y errors, so it should only be used to predict y. So this is definitely worth making a note of. So these regression lines, so we've got the thing about interpolation and extrapolation. So the next key point, the final key point, is that these lines, and they're called y on x lines, they've been calculated by minimising the y errors, should only be used to predict y values. So that's why in this question, predicting the gestation period for a head circumference of 31.6 would be inappropriate. Old spec, we used to have to calculate both regression lines, the y on x and the x on y, and we used to have to realise when we needed to use one or the other. It was a nightmare. So although it's a bit confusing now, it's not in the syllabus, it does make our life a whole lot easier. So just very quickly. We are not going to draw any scatter diagrams. So can I get you, in this question, just to answer question C and D. Again, I'm sorry that this question is from the Year 1 textbook. I haven't got a copy of that. But for those watching, it's on page 65. So don't worry about drawing the scatter diagram and drawing the line of best fit on it. But here's the data. N is our x. I don't know if that's going to help to think of that. And that's our y. So that's our y, that's our x. See if you can answer C and D. And remember, when it says interpret the meaning, you've got to put it into the context of the problem. So C and D in question 1. Again, because this is from Year 1, we're not calculating R, but calculating R should be the first thing. I'm not saying to do it, but before we do any sort of regression line stuff, we need to be able to say that there's a correlation there. Note you're not being asked to make the prediction, you're just being asked to comment on the suitability of the prediction. So, James, in the context of this problem, what is 21, and we're talking thousands, aren't we? So what is 21,000 in the context of this problem?
The cost of producing 0.
It's the cost of producing 0 items, that's right, yeah. So that's your overheads, I guess, isn't it, for those that do economics? So that's, I guess that's your That's your, your heating and your lighting and your staff costs. The costs before you turn the machines on. Okay, so 21,000 is your cost for producing 0 items. And James, what's 0.98? So that's 980, isn't it?
Yeah. So that's wait. I've got a little there.
Remember, the gradient is for every 1 unit you go along, how far it goes up. So
Yeah,
what does
so-
that mean?
So it's, the change in the production costs. Well, 980 every time you produce 1,000.
Yeah, that's right. Yeah, so increasing the number of items we produce by 1,000 increases our production cost by £980. 0.98, but that's in thousands. That's right. Yeah. So Harry, a prediction for 74,000 items, reliable or not reliable?
No.
And
Number one. So one option goes to. No, it would be. Sorry.
yes or no?
Because it would be.
It would be, yeah. So because 74,000, this is 74, isn't it? Is well within that range. 95,000, well outside the range. We've got no idea if they've got the capacity for that, so that's not safe. So we've got the regression line is suitable to predict for 74,000, but not for 95,000. 95,000, it's extrapolation. It's outside the range of values that we have plotted.
Which one was it suitable for?
So the 95,000 wasn't suitable because we didn't have 95 in our range of values. The most we had was 81,000. Okay, one final question then on this. So question 4. And I wonder if this is more of a common sense question. So George, 190,000 would be the y-intercept, so that would be the value of a house with 0 bedrooms. So why might it not be a reasonable statement?
Well, there's loads of different factors, isn't there? Like where it is. I don't know.
Can you see any potential problem buying a house with no bedrooms?
Oh yeah, you've got nowhere to sleep.
Yeah. No one's going to want to buy a house with no bedrooms, are they? So there you go. Yeah, that's it. Yeah, so it's unlikely to be accurate because a house with no bedrooms would be less desirable. So that sort of demonstrates the problem of extrapolation, doesn't it? We are, we probably don't know the values here, but we've probably got data here that's, for 1-bedroom houses, 2-bedroom houses, 3-bedroom houses, 4-bedroom houses. So we're okay making predictions in that range. And this line is the correct line of best. That doesn't mean they've made a mistake. This is the correct equation, but it's only used between the values that we've actually got plotted. Okay. Actually, let's just do one more. Just see if you can give an interpretation of the value of the gradient. Knowledge of the large data set. Well, those horrible questions, aren't they? And then, again, you haven't got to make predictions. You just asked to comment on those predictions. We won't worry about part 2. So give an interpretation. And this throws in a word that I haven't used yet, so we'll define that word. Causal means does one cause the other? Oh, right. Really? Sorry. So the gradient of the regression line is negative. So that's the first thing to note. It's a negative correlation, and it means that for every 1% increase in humidity, our visibility is going to decrease by 106 decameters. So causation and correlation. So if you look at sunglasses sales and sales of cold drinks in Woolacombe on days through the summer, they're probably correlated. But that doesn't mean that people being thirsty means they want to buy sunglasses. Those two things are related, but they're not causing each other. That's a correlation, not a causation. I think there is a causal relationship, because I think if it's very humid, it's raining and you can't see very far. 100% humidity, that's extrapolation, haven't got data. Humidity with a visibility of 3,000, that's using it the wrong way. This line of best fit is designed to predict V, not to predict H. There we go. So we've said we can only do a line of best fit if we've got correlation. We measure that with R. Once we've got a line of best fit, we can use it to make predictions within the range of values we've got, but only for Y values for a given X value. More of this tomorrow.